right? So with this, the idea of MathWorks came, and probably we are one of the very few companies in the world whose logo resembles the solution of a partial differential equation. So I find that quite interesting, right? So today we will talk about how you can model and simulate different applications of cyber physical systems. So we all of us knows that typically when you look at cyber physical systems, they are very complex, and the challenges that you typically find might vary from application to application. So today we find that what we are going to talk about is specifically looking at what is a cyber physical system, what sort of applications do you find when you talk about cyber physical systems, and what are the challenges that are related to that. Then we can talk about how you can use MATLAB and Simulink specifically to address those challenges. And then if you are interested in going ahead and working on any specific project in this area, how to get started. So what is a cyber physical system? So so before going ahead, some of you might not be familiar with, but although we are known for our product, so the brand name is MathWorks, and one of our key mottos is to accelerate the pace of science and engineering, specifically so that engineers and scientists can do their work better and improve our standard of living. So if you look, typically there are two major products that we use. Sometimes when we go to university, people don't know us by the company MathWorks. But when we mention we are from MATLAB or we are from Simulink, often people very easily are able to relate to us. So specifically, if you look here, MATLAB is the platform which is typically used to develop different algorithms. So you can design different algorithms, carry out numerical computations, and it has an environment that can help you in this. There are a number of apps that are there to support getting your tasks faster, and it's a very interactive sort of environment. So it's not just you are writing your programs, but you can actually design your algorithms in such a way that any external users can directly interact with it and get some sort of output. Alongside, we have a platform known as Simulink, which is pretty very much popular, specifically among students who use it for projects and also in industries. So in case of industries, Simulink specifically is related to something known as model-based design. So I'll just briefly touch upon what model-based design is. So using model-based design, you can carry out different simulations, take the simulations, test and verify your algorithms, and then finally deploy it to a particular hardware and see how it particularly functions. So given this background, where is MATLAB and Simulink being typically used? So MATLAB and Simulink in terms of industries, it's very widespread. We go from, if you look here in terms of areas, we are going from aerospace, automotive, even till software and internet, medical devices. So lots of different applications which we rely on in our day-to-day life. So primarily, aerospace and defense and automotive is majorly where it is being used. But as you can see, we have a pretty big footprint in other industries also. So now coming to the original question, what is a cyber physical system? So the name itself gives away. Cyber physical systems are a system where there is a computer connected to an actual physical system. So the physical system here could be represented in terms of different sensors, different actuators, it could be robots, it could be drones. So all these systems specifically are there to help us out. And if you look in terms of applications, pretty much the present applications are in the area of smart grids. Smart grids, I hope you have all heard. Nowadays the electric grids typically are all have different sort of supervisory algorithms governing them. So they are connected, they have data coming into a central computer, and there are different algorithms running on them. Similar to that, there is autonomous cars. So autonomous. So if you look at cyber physical systems, some of the key features of them are that they are able to adapt. So given a particular situation, they will be able to adapt, act autonomously, as well as collaborate uh, in order to achieve a particular goal. Right. So also people are nowadays talking about building different sort of smart emergency response system. So typically, if something happens at a particular place, how the whole there could be an autonomous thing that could respond to those situations is something that people are planning. But more interestingly, nowadays, cyber physical system is being talked about in the context of Industry 4.0. So have you heard this before? So what people are talking about is that taking the help of cyber physical systems, what they are planning is that different industries, specifically manufacturing, they want the processes to be enhanced. They want the systems to be enhanced in such a way that the different disciplines who are specifically into manufacturing, they can collaborate more effectively. And then since there is a lot of data also involved, to take the right data to the right person. So if the right data comes to the right person, then they will effectively be able to take informed decisions. So in this area, one of the key technologies that is also going to play an important role is robotics, specifically AI-based robots. So the concept, if you typically look here, is that there is going to be a number of workers in an environment, but there is also going to be autonomous robots. And using IoT technologies, they will be taking data to a central system. So in a cloud where there are AI algorithms running, different sort of algorithms could churn that particular data. And using that sort of a data, people are thinking of different sort of end goals, satisfying different sort of end goals. Like they can have different sort of optimizations. People are talking about how you can actually take those data and predict when a particular equipment is going to experience downtime. So in this part, if you look, autonomous robots are going to play a very key role. So autonomous robots are going to play a key role in this particular area. And given that now technologies like 5G are coming into the picture, it will be very important that we actually focus efforts to actually learn about how these systems are connected together and have some experience also modeling this sort of systems. So just to give you an overview, I previously conventionally what we are used to is that robots, if we use in a manufacturing setup, and typically the robots there do repetitive tasks, you have to manually program them and set up boundaries. So boundaries because we do not want anyone to experience any harm in those environments. So there is a safety fence needed for that. But nowadays there has been a progress, and currently what people are using now are robots and people in the same sort of environment. So if you look here, it's a flexible sort of automation, and people are calling this cobotics. So there are robots also in a particular environment, and there are different safety related algorithms running, which ensures that the people who are running or who are actually working here are actually safe. So safety is a very critical thing that that remains to be addressed. So this is where these algorithms are specifically addressing. But if you look at the future sort of direction where we are looking at and where industry is looking at, is specifically having autonomous systems. So robots that are in that particular environment who collaborate together by sharing, by learning to actually work in that particular environment. So they adapt and they themselves are able to take decisions by sensing that particular environment, knowing what is required in that particular environment and taking the relevant steps. So just to give an example, this is a particular robotic system that was developed at the German Aerospace Center. So it is a humanoid robot specifically which has hands which actually can do certain tasks. So let's look at how this particular robot is functioning. The video is not running. Okay, let me try. Clicking. Yeah. Just click. It should play. Yeah. So you can see that it is able to act autonomously in an environment and do certain tasks, lifting certain objects. So here you can see the robot is actually able to sense its environment using different sort of sensors. So there are LiDAR sensors using which it is able to sense where the different objects are located as well as what is the surrounding environment. And then taking those objects and placing into very specific arrangements. So all right, I think this gives a sort of idea how it is actually working. And the good thing about this is that for this sort of simulations, so for this sort of applications, you can run the actual hardware. You can actually see it in action and also see the simulation side by side. So you can see the robot responding in real time and catching that particular ball. Yeah. So we can go to the next slide. So what are the things that you are going to need if you are planning to build an application like this? Firstly, very importantly, you are going to need a particular platform to carry out the whole development. And this could be challenging, right? Because there are so many, the tasks that could range could be very complex. So doing everything in one single platform is a very key thing that people working in this domain are looking at. Yeah, this slide. There will be different sensors which are interfacing. So sensors, when I call nowadays, popularly, if you look, there are a wide number of sensors that are available in the market, ranging from image sensors, sensors related to capturing motion, capturing distance from different objects. So there should be a platform from which you can integrate or you can connect various different sensors and then taking that particular data, then using that, perceiving that environment. Finally, given certain sort of actions to be taken in the end, how to carry out a planning task. So it has to plan and decide what it has to follow. And then we can give it some sort of control command so that it is able to follow up on the planned action. So we can tell it that you take an object and place it here and it should be able to do that. Right? So what are the, now given the application that we have seen right away, what are the sort of challenges that you see? So here, what we have done is that there was a survey taken by University of Aberdeen, I think. So it was the Aberdeen group specifically, they have taken a survey and then they tried to find out what are the sort of complexities that you face when you work in this sort of systems. So what is the major complexity that you see? So there are different sort of things that are there. Okay, so starting from early identification, if there are any problems that you have in the very early stages, if you try to build a prototype in the later stages, it is going to be very challenging, right? Specifically, lack of cross-functional knowledge, changing requirements. So among the different challenges, the biggest challenge that people are actually talking about is that designs are becoming very complex. So if you look at the any sort of problem in the domain of cyber physical systems, the designs have become very complex, and addressing them in a way that different teams could work together on those designs is something that we have to look at. Also, very interestingly, if you look at the softwares that are there, specifically in this area, software is also becoming very complex. So using a particular software, specifically a complex software, in order to do these tasks is also a sort of challenge that we are going to see. So what is the answer? So the answer, how to address this challenge, is something we are going to take a note from what our industry has to say. So industries, interestingly, have been using MathWorks product for some time. And if you look at the sort of applications that we talked about, starting from robotics, looking at robotics, looking at aerospace, automotive, they have already worked on very complicated sort of challenges. So the answer that they trust, and the answer that probably can help also us in the area of cyber physical system, is to use something known as model based design. So let me just quickly check how many of you have heard this term model based design. Anyone? Have you heard this term model based design before? Okay, so maybe this is totally new to you, but can you take a guess that what could this mean? What could a model based design mean? Again, the answer is very much in its name. So model based design essentially means that specifically for this sort of tasks, building this sort of complex systems, you depend upon a model. You do not plan and directly build a physical prototype. You actually depend upon models to do most of the tasks, going from gathering what you need to do, what are the requirements that you have, to testing and verification. Every depend upon models rather than building a physical. All you need is a laptop and probably install MATLAB and Simulink, and then you can get ahead. You can actually start building everything starting from scratch to the last part where there is some sort of control algorithm which we converted into code in one single environment. Yes. So now going ahead, conventionally, how people used to do this? Conventionally, we have a problem statement. Let's say we want to build a sort of an autonomous robot. So we will have certain design objectives, we will have certain constraints. So this is where we start, right? So after coming here, let's say I want to build a car. So I will have some sort of objective that how fast the car is going to go. Okay. What should be the total weight of that car? Very similar for robotics also. Let's say I am planning to build a robot. I might have some requirement that what is the eventual amount of movement the arm is going to make. What is the maximum angle that? Next, then we are going to start the design process. So previously, what used to happen here was that different people from various different domains used to collaborate together. So you had department, people from the electrical department, let's say probably people with a controls background to design the control algorithm, and then there will be embedded software engineers who would specifically convert the control algorithms to code, and then go to the integrated testing. What challenge do you think is going to happen if different disciplines are going to work separate from each other? If try to challenge, because groups they will be working on different. They will be working. So the term actually came from So what industry did was that they found solution. So what was the solution that they found? Yeah. So what was the solution that loops they will be? So initial requirements get I think if it's redeveloping what very traditional. So first they have talent, they have talent in digital prototype. The problem is also that if you find any error later on, so you have built a car, you are taking it to the code and you find that it is not giving the performance that you expected. Then you have to come back to scratch. You will have to start designing the car design from scratch. Also, a very of our particular error right in the requirement phase when you are trying to determine what sort of functionality is going to happen, you see that the price that you have to pay to fix that. But as you go into the whole production and then design and then finally testing, the cost to spend much more from their experience, but they chances are that you are going to encounter more than one domains, right? On a robot, you will have mechanical components, you will have certain electrical components, you're going to see computer vision because there is going to be some sort of camera that is there. You are going to encounter something related to AI. So different domains have to come together. So model-based design, since you're working with a model, in a model you can introduce multi-domain simulations. So everything is being done on one single environment. I think one slide back. Yeah. So could you maximize? So if you do everything in this sort of an environment, you are actually going to save a lot of time because there is one single environment. When you eventually go to this stage where you integrate everything, you are not going to face any challenge. Also, you are going to use better design because constantly you can, it's a model. You can run different simulations and compare results. If you are not happy, you can go back and then reiterate. So it's a model. You don't have to spend extra money. It's all a model. You can, in fact, you can actually simulate scenarios which might not be possible in a real environment. Finally, when you are all said and done, you can actually take that particular model and auto-generate the code. You are not manually going to write any code. You can auto-generate the code. So eventually, if going by this sort of a process, you are actually going to do things a lot faster, and it is going to be a lot cheaper also because you are not spending time and effort building a physical model in the first place. That is going to be the last step that you are going to do. Any questions with respect to model-based design? I think we are kind of covering the background. So now we are going to look at specifically what people do. In the industry, they call this sort of a thing a V-shaped workflow. So if you look here, what they are doing is that they are starting with requirement. Based on that requirement, first they build a system level model. So they will have system level specification. Based on that, they will build a system model. So system engineers are going to design how the whole system is going to look like. Robotics, autonomous cars, any application where you look at, the systems are quite complex. So right away, you do not go from specification and dividing the tasks among different disciplines. What you do is to involve a person with a system engineering background who is going to design that entire system architecture. Based on the system architecture, then you can divide the tasks among people from different background and assign the right task to the right person. After that, they are going to design the subsystem. After designing the subsystem, they will try to implement and test it out. So in the V, if you look, the left-hand side, mostly it is about going and building the entire model from the requirement. And the right-hand side is about the testing part of it. So since it is a model, you have a one-to-one correspondence. You can actually compare the subsystem. If you look at subsystem integration and testing, you can do and compare with what was given for the subsystem design. System level integration and testing you can do. Let's see if this works. So system level integration and testing you can do, and you can compare with what was given as the system level specification. And then finally you can complete the whole integration and testing part. Right? So once this is done, then you can actually your whatever you are building, it will have, chances are that it will not have any major error in the very end. Now we go to an example, and probably I'm going to ask you like which step is this in. So what we are going to talk about is, let's say I'm going to build a robot that is a quadruped running robot. So a robot that is able to move on 4 legs. So for an example, or I would say you have heard this now, biologically inspired design. Let us look at how a horse runs and build a robot that is going to run in a similar way. Right? So what we can do on a very simpler note is that when you look at the legs of a horse, we can kind of think that the legs are like an inverted pendulum model. And using that model, we can kind of find out what are the different gaits we can actually model. So specifically when horses run, they use their gain to actually recover kinetic energy also. This is very interesting, right? So muscles are not something which is typically in a human's muscles are inefficient. So it is always good if you are able to recover a part of the energy that you're spending when you're moving that muscle. So that is what horses do. So to build a robot like this, so we can model it like an inverted pendulum. Yes or no? So you can think it's like a spring and there is a mass connected at the other end of the spring. Now what we are going to do? We are going to do a design study. So we are going to do a design study. Going the opposite way. Yeah. So we will have a number of parameters that we will identify. So these are some of the requirements that I'm looking at. That okay, my robot, it will have a length of this much, let's say this much meters. It will have a certain running speed. It will have to support a certain mass. So this is where I am actually gathering the requirements, correct? So now just remember the V cycle. This is where I'm collecting the requirements and finding out what are the design parameters. And then using the spring mass model, we are going to build a very simple MATLAB script. And then we can have sort of plots where I can vary the leg stiffness and look at the sort of gait period with the number of feet on the floor. So I can do very simple sort of behind the envelope calculation. So this can be done in the MATLAB. So we can start with requirements and then we go to the next step. So once we have those requirements, what we can do is that we can take it, we can take the help of a multi-domain environment, such as what we have in Simulink, and build the model of the leg. So the difference with the previous model, if you see here, is that now I am taking mechanical components. So you can see, so there is an upper leg, there is a lower leg here connected by a revolute joint, which actually models the knee of the horse. Then it is connected, the upper leg is connected to another revolute joint, which is like the hip of the horse. So we are modeling the horse, the mechanical in a mechanical way. We know what the requirements are. We are now passing it to mechanical engineers. They are building this sort of a mechanical model. And given a particular environment, what they are going to do is that they might suggest that there are certain inputs that they are going to provide. And they are measuring here, if you look, they are measuring what is the hip angle, what is the hip velocity, what is the hip torque. So eventually the horse, when it moves in a virtual environment, they will get a sort of curve. So this could be the second step where you model a certain subcomponent. So MATLAB has an environment where you can model this sort of mechanical systems. So there is a tool known as Simscape Multibody. So using Simscape Multibody, you can model dynamic 3D systems. So in this particular tool, you will have body elements, so you can build legs. There are joints, so you can build places where it can move, rotate. So this is just for the robotics, but there are different other things also. There are belts and cables, different sort of surfaces. You have different sort of forces and torques that you can apply. And if it is necessary, you can build CAD models of everything, bring it to an environment and connect them together. So Simscape Multibody is a tool that can help you do that. Secondly, once I have done that thing, I will know that what are the angles that are needed for rotation, what are the inputs that are there. So I can collaborate with people from the electrical domain to identify what sort of motor are going to give me those characteristics that are needed with respect to the change in angles, what sort of power consumption I'm looking at. So given those factors, an electrical engineer can collaborate and identify the specific motor that could be useful for this particular application. So this could be actuator selection. So which stage of the V cycle does this correspond to? Modeling the subcomponents. After doing this, the electrical engineer might give me come up like a plot like this, a power plot and a torque on the other side, and then using the data points, they can identify which motor to go for. So how will the electrical engineer do this? So there is also another environment. So as I mentioned, this is a multi-domain modeling environment. So in case of Simscape, you can build model for the electric motors, and then they are connected to a gearbox sort of a thing. So I know what sort of torque I'm getting. So here you see everything is color coded. Color coded means blue part is the electrical part of the circuit. So they are building a circuit where there is a power source powering a particular motor, and the green part is the mechanical part of it. So there is a and there is conversion of energy that is happening from the electrical to the mechanical. So this is where they are going to take up a particular design and then try to validate it, whether what they are expecting they are getting or not. And in the very end, they might be getting this sort of curves, which might be useful to validate that this is what we are expecting or not. So just to briefly let you know, if you are new to Simscape, so Simscape is a multi-domain modeling environment, which is becoming actually very popular in the industry nowadays. You can model different sort of components here, starting from electrical, mechanical, thermal, hydraulic, gas, magnetic, different environments, all with one single tool. And then the best part about this is that whatever designs you are going to connect physically, the equations for that is going to automatically come out. So automatically it will generate the equations for you, and if you want, you can convert these models to code also. So you can take a Simscape model and convert it to C code or other code for deployment purposes. So it's colored according to the domains that you see. So mechanical is green, electrical is blue. So you just have to connect the things together. There is a, in the background, it is going to define the equations, different algebraic equations, and solve it. So just to give an example, how typically this sort of multi-domain models look like. So there are different levels of modeling fidelity also. So this is one way we have perhaps modeled a particular component, but chances are that if you are interested in the very details of a particular model, you might be using a PDE toolbox and try to solve a partial differential equation for that particular component. Simscape is specifically good when you are in the moderate region, where you are not looking at a lot of details, but mostly interested in the system sort of a performance. And for faster simulations, definitely you can use Simulink. So there is a flexibility in terms of what are the environment that you have to build your own model. So finally, what you have to do after building the whole mechanical, if you build one leg, you can take the knowledge and then convert it and build 4 similar legs. So here you can see there are 4 legs that are there, and then there is a supervisory algorithm that has been built in Stateflow, which controls how these legs are moving. And eventually you carry out some tests to find out what is the motor efficiency, how the gates are happening. So this is a model which is already there. So you can see how it is performing in a simulated environment, and you can carry out multiple different sort of testing so that you know that the result that you are getting in the very end is something that you want. So which step would this be? So this would probably be the 4th part, where you are testing out the different sort of, no, this is the part where you are integrating everything and trying to see what sort of results you are getting. Also, it is just not one single thing that you have to look at. There could be multiple different things. So we can actually, after carrying out this sort of design, we can look at different sort of optimization algorithms, or we can run different sort of simulations to find out how different parameters affect its performance. So just looking at how the gearbox ratio affects efficiency. So we can carry out these sort of things we can automate these sort of things very easily. So there is an environment where you can carry out design trade-off studies very easily, because there are optimization algorithms already built into the MATLAB environment, which can help you do optimization very easily. It's integrated. So just a summary of what we have looked at. We have looked at how you can carry out multi-domain modeling. There are certain design criteria that we start up with, and then possibly how to do it in a one single environment. And then finally, we can how to automate support analysis and optimization. So this way, it's much better than going and starting doing the entire thing using a CAD tool. This is a much better way to do it. And this is an example of a university which has done it. I think a couple of years back, there was a team automatons of PCCOE College of Pune, which had actually built a quadruped model starting from some very basic things. So if you look at the very top, they have the inverse kinetic models there. Inverse kinetics means you tell that where specifically in their case, the path that the robot's foot is going to take. So the quadruped's foot, how it is going to move. Typically, we can assume that it moves in a semi-parabola. So if you assume that thing, you can build an algorithm which can back calculate that for that movement, how the hip angles will vary, how the joint angles will vary. So this is the basic algorithm that they designed for that. And then once they had that thing there, they were able to go back and create the mechanical model, where they had actually components, the mechanical components connected together, and then they were able to test it out in a simulated environment. And they had some very interesting results here also. They found that when the robot was moving in a particular place, it was vibrating a lot. So as I mentioned, we are modeling it like a spring, right? So there is going to be some sort of vibration. So doing a few design modifications, they were able to identify that what was the cause of the vibration and also eliminate it. So overall, to build this sort of an automated quadruped robot, they found using model-based design a very easy sort of framework to use, right? And they had multiple libraries here that took into, so they had to think that the thinking part was done mostly by the students actually came up with the whole design, and there were tools that supported them that in that entire task starting from the beginning till the very end. So this is something that we have to look at. Eventually, we learn best by doing certain things, right? So I have a few summary sort of a thing. One of the things that also you need to think about here is that when you talk about this sort of systems, there is also one thing that is very important nowadays is that people are talking also about cyber security. So those sort of things can also be incorporated very easily in a model-based design. The V sort of framework that we saw, you can actually also very easily incorporate aspects of cyber security there. So whatever code that you are generating, code generation is a very important part. And depending upon the applications, you might have to have certain standards that you have to adhere to. Like specifically for electric vehicles, you have ISO 26262. So that part can be very easily taken care by MATLAB and Simulink for you. The second thing to build this sort of a model, we have a number of examples that you can get started with. So specifically with Simscape, if you look, there are very good examples for you to get started. So this is one place that can actually help you very easily get started, get going with these particular tools very easily. Also, whatever the whole environment is very tightly knit, so whatever things you are doing in the environment, you can very easily integrate it. So in the last case, I just showed modeling the robot part. Let's say if you want to integrate AI into your model, in case of MATLAB, in case of Simulink, you can very easily integrate different sort of AI models also with your own model. And you can test out for different faults also. So faults can be introduced. Here you can see specifically faults given for a particular component. For different component, you can introduce faults and find out how the system is going to perform in when those faults are there. And also there is one more thing. There is also an IoT platform that we have called ThinkSpeak. I'm not going into the details of that now, given the amount of time it is going to take. But using ThinkSpeak, you can also take the data that you are gathering to a centered place and carry out different sort of computations. So it is there is also a platform that helps you gather those data in a central location and carry out different sort of prototyping tasks. So how to get started? So this is very key. A major thing that I want to say is that often just starting from the tool side might not take you very far, because we work best when we have a problem at hand. So I would suggest very much like how the Pune team did, try to compete. So try to enroll into competitions. So this is specific for students. There are different competitions that are sponsored in India and abroad. So take a part in those competitions. So very similar, like we have a competition now ongoing in the area of mini drones. So which is being co-hosted by IIT Kanpur and Society of Aerospace Engineers. So here you can learn to design and build flight control algorithms using mini drones. And there is going to be some very interesting round. There are going to be a simulation-based round and a hardware deployment-based round. So when you participate in these competitions, this is when you know what is the requirement you can very easily gather from the problem statements given. And then I believe if you participate in these competitions, you actually will know which tools to use best. And in the end, you will also get a lot of recognition for your work, which is eventually going to help you a lot when you transition to the industry. Also, as I mentioned, MathWorks tools are built so that you can actually design different complex and robust softwares. So specifically, there are environments to build and test different algorithms like Stateflow. We have MATLAB, where you can design different sort of algorithms, and then there is Simulink, which is the platform for model-based design. Right? Also, to get started, there is a number of So for people who are very new to these things, there are a number of resources which you can cover at your own space. So we have MATLAB Academy, but there are a number of courses which can help you get started in this area. So let's say you are new to Simscape, like what I saw in many of you. So you can go ahead and do these courses, just run in the browser, and in the very end, it takes around a couple of hours to complete some of the basic courses. You are going to also get a certificate in the very end. And lastly, feel free to reach out if there are any questions with respect to competitions, anything around curriculum, anything around research. So we have a team now. We have multiple dedicated teams, so we can connect you to them. So they will be actually very happy to take you ahead. So this is where I pause my presentation. If there are any questions, any comments, I will be very happy to hear from you. Yes, sir.
Explain the design aspect of the dynamic system. System in which communication aspect is also involved. In that case, you may have to go for post simulation. Is it possible to have a post simulation right now in MATLAB platform?
That's a very relevant question. So in case of co-simulation, we also have number of environments where you can test this out. So virtually, it's very easy to test systems. So there are virtual environments for testing automated vehicles. For robots, we have the gazebo environment where you can give the robot certain tasks, and it is going to perform those tasks in those virtual environment. And if we are so interested, we can actually combine it with the hardware also. So at the same time, we are going to see the virtual robot mode as the hardware, which is very similar to the concepts that people are now talking about, like a digital twin sort of a thing. So same sort of behavior we are going to see in the simulation environment as well as in the hardware also. So I think this could be a very interesting area to actually also look at.
In addition to hardware, what I'm looking for is the communication network.
Yeah.
Is it possible to simulate the communication network also along with the dynamic system simulation?
Yeah. So yeah, that aspect is also there. So there are different sort of protocols also that you can actually very easily simulate. So there is, I think, a particular toolbox also for that. I think there is a communication toolbox also that can help you simulate the communication part.
Thank you.
So thank you, sir. That was a very good question. Any other questions that you have? If not, maybe I will just check. How many of you are participating in any competition? Maybe I will just see. Any competition that you are participating in? Any clubs that you are part of? Robotics, automated driving? Yes. That is really good. That is good to know. So what are the clubs that you are part of? Student clubs? That is a very good area. Marine technology. So you must be working with underwater robotics vehicles also, applications also. So really good to see. I'm not sure if you know the news. I think there are Indian government organizations also working on projects. Very recently came out in the news where there will be drones coming out of submarines. So it has to be able to function both in a water environment and also able to function in the aerial environment. So there are some very good applications that are coming. If you are working in this area, definitely you will see some very good opportunities. So all right, any other questions online? Do you see any other questions online? Okay. So thanks a lot, all of you. Yeah.
Yes, like you're mentioning about the state flow on-ramp courses, right? So how the state flow diagrams can be related with CPS concept?
So this could be more to do with the supervisory algorithm. So I think specifically, let's say for system of connected electrical generation sources and distribution sources, you can design a sort of algorithm that could show you like which option to go for which sort of scenario. So in the case of this one, so typically how we used to do it in our programs, we used to draw a chart that okay, if this condition is there, then if yes, then this thing is going to happen. If this condition is there, then the other thing, if it is no, then the other thing is going to happen. State charts are very much like that. So let's say there is a particular condition, a particular temperature, which is let's say at a particular value, let's say 100. So I will have that algorithm say that if it is temperature goes beyond 100, a fan is going to move. If temperature is going to go beyond 150, there is going to be AC, and if perhaps temperature goes beyond 400, everything has to be shut down. So there we can do it graphically, and when we implement it, when we connect to a real system where there is a thermocouple connected measuring temperature, and then there are certain actions happening via controller, I can see in the state chart which state it is currently in. So for a complex system, it will be very easy for us to visualize that how the supervisory algorithms are working. So those loops, control loops are very easily visible there. So that is one of the benefit, and the other benefit is definitely can convert it into code. So something that is graphically easy to understand and also convertible is to code can be very useful for a particular application. So Stateflow people are using for supervisory sort of algorithm, designing battery management systems, designing supervisory algorithm for a particular autonomous system. So those sort of applications that could be useful for Stateflow. So I think for students who definitely can take a look at Stateflow, chances are that you can very easily use it for any project. So thank you for the question. So if there are no other question, I don't know if I'm good with time. Good with time? Okay. So I thank all of you for being a part of my interaction, and it's very good to see you all physically. So definitely, I hope all of you have got some sort of takeaway from this particular session, and that actually is eventually able to accelerate the pace of your science and engineering. So thank you all of you. Have a good day. So slides, I think I will share with Professor Devraj, so he will be getting my slides. So thank you.
Yeah, we indeed thank Dr. Devan Singh for gracing this event with your physical presence. Because in SRM, we have a very close contact with Marcus, in which the team is supporting SRM technical part in conducting events and in conducting especially the 2-credit courses, real-time edge computing with MATLAB. I hope many students in this hall also are undergoing this course. So along with NVIDIA and SRM, the course is being happening here. And in other than that, they used to conduct many workshops, and so many technical support is being provided from Marcus in many ways. So in that sense, also altogether, we thank Dev and his team, especially Mr. Vinay also, for arranging this kind of session in physical mode also. And now I request Dr. Devraj sir to felicitate our speaker, Dr. Devan Singh.
Sir, I'll take small snaps.
Speaker on. He is going to introduce first.
Co-host mode.
Mute button.
Hello. It's enabled. Hello. Hello. And now I request Dr. Vijay introduce our next speaker, Dr. Gaurav Purohit. Dr. Vijay, sir.
Yeah, thank you. I hope I'm audible, right?
Yes, sir. Yes, sir.
So thank you very much to our organizing committee, and it's my real pleasure to introduce my friend Dr. Gaurav Purohit, who is currently working as a senior scientist in Societal Electronic Group of CSRC Pilani. He has completed his master's and PhD degree from BITS Pilani, Rajasthan. He was also a visiting project researcher under Japan Asia Youth Exchange Program at Hiroshima University in 2017 and 18. He has worked in various projects, which includes data analysis for air quality monitoring, IoT-enabled cloud communication for structural health monitoring applications, AR/VR for Jigyasa Virtual Labs, and NAND flash memory controller design. He has published many research papers in various international and national journals in the subject matter of implementation of wireless baseband architecture and machine learning. Today, he will be talking about intelligent data analysis for air quality monitoring. Hopefully, it will be very fruitful for all the members who have joined this talk. Thank you. Over to Gaurav. Please unmute him. Yeah, Gautam, can you please unmute him?
Yeah, thank you, Vijay. Am I audible?
Gaurav, over to you now. Thank you.
Yeah. Yeah, so very good afternoon to all on the dais and my faculty members and the dear students. Without wasting much of time, I just click to my topic directly. Today's topic is intelligent data analytics for air quality monitoring. And as we know that the theme is related to cyber physical system, simulation and modeling. So this is one of the use case which I am presenting today. I would like to take my presentation in dual mode. That is, I will be live throughout my presentation, but first few slides will be directly live, and after few slides, there is a recorded presentation. I have done this because due to internet issues, I hope that you will enjoy in both the mode. So first of all, as the theme is related to cyber physical system, so I thought I will start with the people who are beginner level, and if they are on the intermediate, they will also enjoy the same. So what cyber physical system? Cyber physical system means an intelligent system. And that's why the topic is revolving around intelligence. So it is a system which integrates the sensing part, the computation part, the control and the networking of the physical objects. These physical objects are near to our infrastructures and connecting them via internet and with each other also. So here what physical means, some tangible thing, that is some environment and some physical sensing devices. And then cyber here means computational and communicational units. So if you see this figure, the cyber world is having three main basic units, that is the control block, the computation block, and the communication block. And the physical world, which we all know and we usually work on, that is embedded system, the physical systems, and then the system sensors and the actuators. Collectively, the system has a potential to reshape our world with more responsive, precise and reliable and efficient systems. So these systems will enable the coming world into the smart device and system. So if I take this slide into a nutshell, it is CPS is about intersection and not the union of the physical and the cyber world. Basically here intersection is actually collaborating the computational entities. So why CPS is so popular and we are gathered here for such a discussion? CPS is having three fundamental units, the software side, the control side, and the system side. And if you see, they have their own boundaries. And if you want to cross this interdisciplinary boundaries, we need to realign ourselves with new fundamentals. We have to recreate new technologies around them, new tools to develop around those things. And then obviously in academia and the training to be restructured. So coming upon the CPS layer and interactions, as I told you, the three blocks on the upper figure first, there is a physical layer, there is a platform layer, and there is a computational layer. Okay. So when we go for computational layer, each computational object is actually connected, and they are connected for the refinement and the compilation of few tasks. And there is an abstraction so that you can easily share with the platform layer. Middle layer is a platform layer. The lower layer is the physical layer where all the sensor, actuator, and other devices are there interacting to each other. Okay. So when you go towards the CPS and its model-based design, three main features will come. That is the software models, the platform models, and the physical models. So what is the challenge? The challenge is how to integrate these models, which lies in the cross domains, and there we require the interaction. So how these interaction can be understood from one domain to another domain and can be managed and controlled for an appropriate application. So today's use case is around that particular thing. The fundamental slides have already been laid down. Here I will easily say that into this picture, the cyber world is giving you user inputs, the parameters, the behavior, and the adaptations. The things required to be simulated and given to the cyber world to be used for them. But for simulating a specific data, you have to gather it from the sensors, from the physical world through the actuations and to the sensors, and compare them in both the worlds. So what is the physical world for this appropriate use case? That is air quality monitoring. So I have chosen few sensors, that is particulate matter 2.5. This is size in UG per meter cube, and PM10 and carbon monoxide, nitrogen and NOx, and temperature, humidity as an physical sensing from the environment. Though environment depends upon the meteorological data too, so we have chosen the wind velocity, the cloud cover, the rain, humidity, etc. So this is a common example which we usually see in day-to-day world. Nowadays, Windows is also enabled the quality of air as in the dashboard. So this is basically an air quality and its analytics for proper monitoring, computation, and control, and giving an example of artificial intelligence in CPS. Before going to the second mode of the presentation, I am just telling you the deployment approach. So we have taken Depot Center of CSIR Siri as in our geographical region, where we deployed participatory nodes, where we have vehicles mounted with such nodes, which is shown in the red box. The smaller one is in wristband, and another one can be put on any device, or you can say vehicle. Whereas S here means static, which is having a specific longitude and latitude, and they are mounted on the traffic poles. The communication protocol laid between them is Bluetooth, Wi-Fi, and LoRa modules. Now there is a concept came edge computation and cloud computation. So edge here means which is just at the boundary of the sensor devices. So data being collected from different participatory nodes for a specific reason, they will be gathered, averaged out, and sanity of the data being done there so that this task can be saved and not be done for pre-processing at cloud center. So cloud is one and edges are more here. We have one more cloud at our initial Delhi center, which is not now more here, but the Delhi center was having an AI based computation center there. So we gathered all the data and posted it to Delhi station. The aim is to give the appropriate app to an public so that they can easily see the current scenario of the pollution at what they are at the street level, at the block level, and then giving them abstract level of heat maps so that they can route their path from their source to the destination, not only in the minimum traffic, but also for the minimum pollution or minimum resilience path for both pollution and the traffic. So here, I am just telling about from the basic that what is the clean air and how we have gathered the data, and then how we model the parameters in a recorded form. So I hope I will be live and you will enjoy the same. I think the sound is not appropriate. Am I audible? Any participant, can they tell me? Hello?
Even though no single global standard for clean air exists, but we have the air even though no single global standard for clean air exists, but we have the Air Pollution Act, which says the prevention and control of the pollution since from 1981 for and clean air. Also recently, our ministry has launched NCAP, that is National Clean Air Program, in January 2019 with the aim to achieve a 220 to 30% reduction in particulate matter concentration by year 2024. What air pollution means? The air pollution refers to the release of pollutants into the air that are detrimental to human health and the planet as a whole. You can see in the picture a vehicle which is having a lot of source of pollution, and these pollutants
Co- Coordinator, please, can you tell me whether you are getting the sound of presentation?
Yes, sir, we can hear your voice.
Okay, thank you.
are the primary pollutants combining carbon monoxide, carbon dioxide, sulfur dioxide, NO2, and other most hydrocarbons. And the most preciously, these suspended particles, we can say particulate matter, or in short PM2.5 and PM10, where 2.5 and 10 is the size in microns. These also give the secondary pollutants. You can see the main source of primary pollutants like PM2.5, PM10, how they are governed. What are the actual source which gives you NOx, CO, PM2.5 into the air? We can see clearly in the picture or in a GIF diagram that the vehicle, aircraft emission, diesel generator, road dust, concrete batching, power plants, and mostly the domestic fuels with the vehicles create this primary pollutant source. How do we know if an air quality is poor? The air quality index tells us the quality of the air. In short, AQI is a numerical scale used for reporting daily changes in the quality of air of your local area with regards to the human health and the environment. It indicates compliance with the National Air Quality Standard. So AQI is an overall scheme that transforms individual air pollutant, example sulfur dioxide, carbon monoxide, and particulate matter 10 levels into a single number. So you can see a picture here. This is the air quality index for India, which is having the categorical labels like good, satisfactory, and the corresponding mapping into a value of a numeric. So there is a range of 0 to 50 which governs a good label and the health concern of a public. AQI relates to health impacts, and citizens can avoid the unnecessary exposures to these pollutants. From the Central Pollution Control Board and in the Gazette of India, it tells us the AQI and the index governing scales. How we can formulate or aggregate this AQI? This is a good question. That air quality index is defined by the weighted values of individual air pollution related parameter. For example, these are the pollutant concentration into a single number or a set of number. The result is a set of rule by the given equation that translates this parameter into a more simple form by means of numerical manipulation as shown below. The figure shows the two steps. The primary steps is from the environmental measurements using the sensors. These pollutants come into a step 1 and governs their individual indexes with a given equation of two breakpoints and their corresponding lower and the higher values, giving rising to I1, I2 and In as shown in the subindexes. By taking these subindexes, we can do an aggregation of these indexes. Here the aggregation means the maximum of these contributes the direct value of AQI. It sounds very tricky, but you can see a simple diagram here for the calculation of AQI. Here you can see you have to say the station, city and a state. All the pollutants concentration except CO are in microgram per meter cube. Also, an important factor come into the concentration is you have to do an average for a day or for 8 hours or for 1 hour sometime. It depends upon the nature of the pollutant. Usually SO2, NO2, PM2.510 and PB and NS3 takes average of 24 hours. Sometimes they are monthly averaged and sometimes they are seasonal or yearly averaged also. For a given Indian standard, these are a fixed threshold values which are shown in the row number 2. Ozone and CO are those pollutants whose averaging are either for 1 hour or for the 8 hours. This diagram shows that the categorical values of AQI and the corresponding band, whereas the concentration range for different pollutants has been given here as per Indian standards. These color codes are given for public who can easily interpret the level of the pollution they are exposed with. By giving the certain values of the pollutants taken from the nodes or the sensors and then calculating the step 1 as shown in the last slide, we calculate the individual sub-indexes. And then you can see here, since PM10 is having the higher sub-index, the aggregated step 2 contributes PM10 as the major pollutant and governs the final AQI, that is the air quality index, to be 140. My use case includes our national capital territory, that is New Delhi. And the reason of including that into our use case was, it is the second leading megacity in the world as per the data booklet of UN, and it occupies almost 1485 kilometers square area. It is the largest urban agglomeration in India with 1.68 crore residents, exhibiting a decadal growth of 21% and with a density of 11,297 persons per kilometer square. Here the temperature ranges from 4 degree to 10 degree in the winter and 42 to 48 degree in the summer, which gives a semi-arid climate contributing 5 major seasons like summer, monsoon, short post-monsoon, winter and pre-monsoons in a short band of given months. There is a surprising fact that NCT includes a total road length of 33,000 km with about 864 km which is having signal road and 418 kilometers as a blinker traffic intersections. There are 6.93 million registered vehicles on the road by 2011 and there is an expected increase of 25.6 million by 2030. You can see the millions of vehicles are running on the road. That definitely contributes pollution to the city. But we have only 24 air monitoring stations operating in the NCT area from the Delhi Pollution Control Board or this Central Pollution Control Board. There are 10 to 12 suffer stations also there. What suffer station means here? System of air quality and weather forecasting and research. So combining both, we have almost 40 to 45 stations working live every day. So the map allocating this suffer and the CPCB stations, map showing the suffer and the CPCB node stations. Here you
Actually, I'm getting an echo.
see that these maps have the dots, and each dot is a static device which is having 13 sensors to take the primary pollutants and tell the readings. Similarly, we have the suffer stations like in the Wajipur, Ashok Vihar, and etc. So there is a link given here where you can go and check the suffer station live monitoring station with their real-time data. These are the geolocations of these monitoring stations. That is almost 34 stations from Central Pollution Control Board and 11 from the suffer stations. There's an interesting story of this suffer observatory network is during the Commonwealth Games. So there was the first time when India was having this Commonwealth game in few years ago. They planned few of these suffer stations for that, but they are now still working in parallel to the CPCB and giving us mature data of the pollution. So what exactly these nodes do? These nodes are actually for the data dissemination, and there is a mechanism that using this GPRS they are having this sensor nodes, and these sensor nodes are actually taking 13 different pollutants, specifically PM 2.5, 10, ozone, CO, NO2, benzene, methane, and non-methane hydrocarbons, sometimes some VOCs like benzene, mercury, etc. They are also taking these meteorological parameters including UV radiation, rainfall, temperature, humidity, wind speed, wind direction, and solar radiation. So what is the step first to be attacked? So step first was the designing of a crawler to make an Indian database for our smart city project. So you can see that why we are having crawler, because these two different agencies have different data base, and we need the entire data set at our own place. So we developed a crawler which can wait for a specific delay from the secured site even, and uh, that can be take an appropriate data at a frequency of either 15 minutes or hourly from CPCB site. So this development was unique because sometimes these databases are pre-processed by these regulatory authorities, and sometimes they are not available in any form on internet. And similarly, this meteorological data which we have crawled from these stations, they are sometimes missing values, they sometimes having NN values. So in conjunction to that, we use this Indian forecast data from IMD government.in website, and also from private websites like Daskai and sometimes some other Google websites. So we collected temperature, humidity, cloud cover, pressure, dew point, measured wind speed and its direction, and other likewise important data. So if we see the website of CPCB page, we can see here we have to tell the state name, then the state itself, then the form of the report you want to produce, and then the specific date from start to the end, then the criteria, that is either hourly or 24 hours, which parameter, and then when you click it, you can download them in a form of PDF, Excel, and Word. It means that you can have CSV format of data for your pre-processing or for data base management, but you need to come across with many challenges, which I will show you in a few of the slides. First is, whenever you refresh this page, you will have an captcha verification. So if you make a bot which can do a captcha verification, itself is a challenging. So first challenge which we met was enabling an captcha to crawl with bots. Okay, and then when you crawl the data, you have plenty of folders, and in each folder you have monthly or yearly Excel sheets which having millions of rows and columns. And even you can see here that when you have more than 13 parameters, only few are showing in the column wise data. Others are actually placed under these rows. Where these rows ends, other sensor data will start. So you have to manage the Excel sheets by writing few Python codes so that you can manage the all the data in a single column and row format, or you can say a matrix format, which requires for data pre-processing. Another challenge which we met was here is, if I will zoom it for you, you can easily check that this is actually data plot from the Dilshad garden. And if you see here, what you will see here is these are the 6 or 7 major pollutants from their specific ranges, which crawled from 1st of January 2018 to complete year. And you can see here PM 2.10 and PM 2.5 are actually not available, and even ozone is not available. If you go into another plot of ITO, which is another location of your node, you can see for at around 6 months you don't have data, and even you have a missing data here also for NO2 and for PM also somewhere. So that was a challenge to make an you can say prediction model for Indian scenario for the major city like Delhi, where the billions of vehicles are running on the road. There is a heavy industrialization and heavy manufacturing, and you can say growth rate due to the building management is on, and fly making and flyers and all are there. So there is an clusters of pollutants available everywhere, and you can see the fog and smog everywhere with the data which is you can see on the board of my system, that missing data. So how to combat with these problems? And there are plenty of stations where I can say here is the if I zoom it again for you, it's a Mundka. So you can say there is no data. So the primary food for your algorithm is data. And if you don't have a standard data, you will land into a model which is not working for you. It will learn something and it will predict something else. So that was a challenge. If you go for meteorological data, the same problem. You don't have data, or you can say missing data for few months, and there is a null data or NaN data for few complete weeks or months, and the same kind of things. So that's why we have chosen 2 to 3 websites so that we can accumulate the meteorological data in an average and found some suitable method to interpolate using IDW, inverse distance weighting, for multivariate weighting methods. And we can tell you what we do in our modeling. So these are the glimpses of the data from 2018 to 2019. The scenario won't change. It is still like that only in India. So now it's a surprising that you have a billions of vehicles, you have very few limited uh, data source, and now you can see when I have SO2, you have a missing data completely. So that was a plot, and this is how we first put the things, and we see we'll first fill them with zero and then with mean value and with different clustering algorithm. So for our use case and for proper standardization of calibration of node, we deployed few static nodes at identified location for our own campus like Pilani, another campus New Delhi Narayana Center. So you can see we have procured, this is off the shelf from Bosch, which is a well-known company, is having a smart city in Pune challenge winner for these static nodes. So same with an IIC campus is also having such kind of nodes. So we procured these few nodes for our use case to calibrate our own node. What our nodes are is a social sensing nodes we have developed in our lab prototype models. We are having few sensors like TGS24424 for CO, CO2, TGS4161, DHT22 well-known sensor for academia, and PM2.5 SDSO21 for PM2.5 and 10. So we developed lab prototype having LoRa, Wi-Fi, Bluetooth, such kind of things to have an app, Android app like things. So, and this is the final low cost sensor development. This is properly having PCB fabrication, handy modules can be put on a motorcycle or vehicle like car or some you can say crowdsourcing model which can be developed around these wearable modules. And these social sensing nodes are having these 5 to 6 sensors and having BLE, Wi-Fi and LoRa. All the three kind of things are now available with our nodes, and have an app which can show you the current status at every 15 minutes, and even there the GPS locations. So using these nodes and the CPCB and Suffer nodes, we have contributed to a data set from entire at least 1 to 2 year. Okay, and here we have chosen only 13 stations. Why? Because these are the stations of Delhi which is having lot of missing data. So what we have done is we have chosen those stations only which are live throughout the year, and they are not giving any observations which are completely outlier kind of thing. So after managing 13 nodes, we found that okay, these nodes can be taken at a frequency of 15 minutes, and we have no drop instances, and overall 74,000, sorry, 7,43,000 instances are there, and the average PM and PM10 was a major pollutant among all these 13 stations in Delhi. So we have directly taken the averaging of these two pollutants as a source pollutant, and we governed our AQI near to this PM pollutant only. To validate our own model, we have chosen another data sets from Beijing, which is freely available on the Google network under KDD challenge of 2015 to 2018. And we have taken the meteorological parameter. Major meteorological parameter was wind speed, wind direction, temperature, pressure, and humidity. So what the first step was to crawl the data from these 13 stations, make few static nodes at our own lab prototype, calibrated in collaboration with Bosch, and then put it into the social crowd of Pilani and Delhi near to our labs to have more data near at a street level. Then we do the data imputation, that is we have to remove this NN or zero values at every station. Many missing values and outliers were there. So isolation forest was basically used for outlier detection, and you can read much about this isolation forest. To handle these problems, uh, for interpolation, the linear interpolation and ML based algorithm like KNN, K nearest neighbor algorithm was used to fill the missing values. And usually this KNN algorithm works best for data imputation for our as well as the Beijing data set with and even sometime we have used smoothing function to remove the outliers. So this diagram shows that the raw data before the data imputation, and then the linear interpolation, and then the KNN when k equal to 5, which shows pretty well interpolation compared to the first and the second diagram. Then we did some exploratory data analysis. The reason for exploratory data analysis is when you develop an air quality model, you can deal with a non-stationary kind of problem. Non-stationary here means that the data is actually in a spatial due to dispersion of pollutants, and temporal due to change of certain pollutants at a certain level. So the exploratory data analysis is important because it tells us the nature of the data and governing the type of algorithm you apply for modeling. So this analysis give you the seasonality, trend, and distribution of your complete entire data. We worked on few of them are that state model, which gives you the mean, mode, median, kurtosis, pickedness, etc. Then we use the decay Fourier test, or we can say augmented decay Fourier test, which is based on the unit root test. And another kind of decay Fourier augmented test is like KPSS test. That is again
From where you are
on the
doing
unit root test. We worked on resampling and the Granger's test, which is commonly known as causality test. I will explain you what these tests mean for us and the data we have provided for these tests. So we have taken here an example of Ashok Vihar from CPCB station. So if you see this data, this is from January 2018 to 2019 up to 10th month. So it's more than 1.5 years. If you see this data, it's a very vague. You cannot see the trend, seasonality, and residual or mean stock value. But I have pointed here two places. So why I'm pointing here is if you divide these pointers and enlarge them again, you can easily find the trend, seasonality, and residual. So this is again the similar kind of plot in parallel to this plot. I am just actually enlarging or zooming inside. Okay, I will come to this point within a few minutes, but before that we went for ADF and KPSS test, and both says that it's a contradictory. One test says the data is stationary. Here I'm encircling it, and another is it is saying that it is a non-stationary. So it's a very complicated case to assume whether the data is stationary or non-stationary. Then we went for the resampling. So if we go for resampling, you can see here all have a peak values in between to October to April, and we have a Diwali festival as well as Parali burning near to Haryana and Delhi. So and we have a satellite images for that also. But science apart, we can see here there is a peak, and the peak says that instead of the entire data set, if we go and compact on October to April, we can find something surprising. So we went there, and then we find that after resampling, there is a kind of trend which shows the non-stationarity of the data. So this is that part where the model can learn most and can predict the trend for different seasons. So this is how KPSS makes the confusion, gives the another test called resampling, and fly back to the trend seasonality simple test by enlarging into those months where you actually get the trend of the data. Another test which we have went with is the Granger test, which shows the causality, how the dispersion mechanism or the spatial contribution of pollutants at a certain station affects the next neighbor stations near to it. So as those 34 stations with geolocation, which I have shown you in the earlier slides, are effective now. So if Punjabi Bagh is the station, the 9th, 13th and the 3rd in that the row number, you can go and check the name of that particular station. is affected. So if there is an higher wind velocity or the wind direction changes, the dispersion phenomena of Punjabi Bagh affects the station of 9, 13 and third station. Similarly, for Anand Vihar, we have checked that 9, 3rd and 13, which says that Punjabi Bagh, Anand Vihar and 9, 3 and 13 station are very close to each other as per the geographical system. Having all these data imputation and data analysis, we come to a model which says that okay, we'll take two kind of data. One is the time series data of a local station and the time series data of a neighbor station. These neighbor stations will govern the spatial correlation for this particular local station. What I mean to say is, let A be the local station and B and C are the neighbor station. Then the AQI governed at a station A will be through the time series modeling, the time series data modeling of a station A plus the effect of the dispersion through spatial of B and C. So what we do is we take the temporal modeling for this local station and the neighbors are contributing the spatial correlation. Here the spatial correlation are based on the causal are based on the simple inverse distance weighting and the correlation factor. They are actually sectorized. So you can see here the 4 sectors. It means all the 34 stations are now sectored into the 4 submodels. What I mean to say here is the spatial correlation can only be taken if B and C are near to A. If they are farther away, we will remove them because they will unnecessarily increase the features which are not directly correlated to the local station, and that will reduces the number of feature and therefore the complexity of the model. So the model in real time will be happily runs if you have lesser number of features and more data instances which are relative. Since we have a local as well as a spatial predictor, we require the prediction which actually aggregates these all the submodels, learn what exactly going on into the entire city, and then give you the final AQI for a certain reason where the station exists and sometimes it does not exist. It means there is a center point between A and B where you don't have a station, but using these relation you can find the AQI for that particular city or a block. So the spatial sectorization has been shown in this particular picture, where the first quadrant is having only 6 important stations with their geolocation, and these are the actual distances from station A to station B and at station C likewise. I have not shown the fourth partition because the remaining is the fourth one. So if you know the complete set of the station, the fourth one will be the odd among them. Now we are going to a temporal modeling. So what we have done is we have put on a train data as well as a test data. So for 24 months for 13 station, we have taken the train data. For first experiment, we quarterly divide the train and test data, and March, June, September and December are taken as an test data because these are the months comes into the window of different different seasons. Second experiment, which was the successful one, where we have taken the 20 days data for training of each month and remaining 10 days data for the test. Here we use multivariate regression model from the scikit-learn, and we use the lasso model for removing the overfitting with 1,000 iterations on the training set. We have taken alpha value as 0.1 and cross validation set to be 3 and other as a default parameter as the model is from scikit-learn. Second one was the spatial predictor, where we have used the MLP. So here there are hidden layers with a size of 100, 64 and 32. The weight initializing method was Glorot normal. We have an activation function, rectified linear reloop. We have an Adam optimizer with an momentum and learning rate at 0.001. We have a batch size of 128 and epoch size 250. We use L2 weight regularization for removing the overfitting. As I said, the temporal and spatial. So we have taken a prediction aggregator which dynamically aggregates the inflection factors like change of velocity and change of wind direction, and then it predicts both using SVR as an final one. So we predict for 7 to 12 hours, 12 to 24 hours, and 24 to 40 hours, 48 hours window with a mean and max values, whereas 1 to 6 hours as a continuous prediction. So overall, we do a 24 to 48 hours of prediction in advance with this model. So we use different aggregators, but the final one was SVR. That's why I wrote improved aggregator results for New Delhi. So this is the first star for Jahangir Puri, and here you can see the actual versus predicted plot, which are very closer to each other. And I am plotting the first star 1000 instances at every 15-minute interval. This is the first star for Anand Vihar, and the results are pretty cool. This is the second hour Narella's result. This is third hour for Narella, fourth hour for Wajipur, sixth hour for Wajipur. So these all are the continuous predictions. If I have checked the same thing for Beijing data, they are also continuous prediction from 1 to 6 hours and showing the station number as an 1004, which was given in the data set. So this is first hour, this is the second hour, this is some other station second hour, this is some 1005 station at third hour, and likewise. So if I come to the summary of the results, the temporal and the spatial predictor, it shows the R square score and the mean average error, mean absolute error. So first one is showing you the only spatial model that is using IDW and ANN as a modeling algorithm. Whereas second one is an MVR for a temporal. So you can see here, temporal, that is a local predictor, is good for any station, whereas a spatial contributor is having a lesser score. Similarly, the benchmarked output for Beijing datasets are 69 and 70. Though we have less number of stations than Beijing, but we have more number of instances, giving a good learning accuracy. Then we went for a random forest, but that value didn't increase much. That goes to 78. Final version was spatial, temporal, and predictor with sectoring and without sectoring. So after achieving 87% of accuracy, it was pretty difficult for us to move to another higher level. And we are closer to 90% of accuracy with the validation and test. And the MAE to be an error to be at a ratio of 36, or you can say 36 units. So though Beijing is having 80% of accuracy, but the average error is very less. So as this MA increases more, the categorical label which you have set earlier jumps the window. So if you have an error of say 60, you can miss even a label. So lesser the MAE for you, better it will be. So instead of this only continuous R prediction, we have given you the entire slot, that is 7 to 12, 12, 13 to 14, and 24 to 48. You can see here the proposed aggregator loses its 90% accuracy to this 52% only, and even the MAE is very large, because we are only predicting here the mean and the max values. So you can see here that the accuracy for continuous prediction is good one, whereas it loses by many units when it goes for higher one. So that means that our data standardization is a need of R. We require many stations and Indo collaboration, so that they can be calibrated mutually by either by SAFAR or CPCB. That is the most powerful agencies who are actually controlling the pollution of the cities. And then we have those data accessible so that we can work upon them and increase the accuracy. These are the few plots for individual stations with the accuracy and the loss, average loss and average accuracy. And so this is for third hour, this is for the fourth hour, and this is for fifth and sixth hour. So what actually they are telling you about the first 6 hours accuracy and the average loss. So that was all about the pre-lockdown data, and suddenly the COVID, and you know what we are now. So you can see the state where the Delhi was having the Yamuna River and India Gate or Memorial Road on the October 17, 2019, and what happens on April 8, 2020. You can see the fresh pictures. This shows that there is a clean sky and everything is clean. It's not because of the camera lens and all. The same camera has been used for both the pictures. So you can see here the status of PM 2.5 and 10 concentration in the pre-lockdown and during the lockdown period over the NCT Delhi. So you can see from the month and the dates that what was the color coding, and here color coding shows you the categorical values. So it was as high as 176, and it fall back to the bluer one where you can say the lower one. So at around 60% to 70% reduction has happened during this 1 month lockdown period, and that data was tremendous and was unpredicted by any of the model available till date, that what happened during these days. And such kind of data can now be so effective for us to learn, which cannot be possible another time in history. We can say undoubtedly that this data is so important to us, and we have crawled during those days. And that was a miracle that we get such kind of classes even, which I have not seen in the state like NCT, with the pollution level of 10, 12, and 15 even someday. So if we have plotted some of the models with the pre-lockdown and during lockdown phase, and you can say this is the air quality standard threshold, and they are going below par during the lockdown phase. And now since the lockdown unlockdown 5 is started, so it's again going high. It's a bad news for us, but this is 24-hour average for PM10, PM 2.5, NO2, SO2, CO, O3 and all. And this is the overall AQI, national AQI, which says that during lockdown we are completely in the good zone. We were breathing fresh air at our home, though we are afraid of the COVID and all, but the nature was blooming. So this was the web app for the Climo stations from the Bosch, which shows you the color coded and the values with a meter called satisfactory and unsatisfactory. What are the labels usually? And this is the Android app which we have made at our lab, and which shows you the the Pilani region and Narayana region during before lockdown. You can say 169 values, and today it is around 50 only. So the aim of this Android app was it will tell you the route map and the heat map of the entire India. So what exactly it shows you all the stations having the color histogram of the current AQI value, and these are the two nodes from Pilani to Delhi. And if you can choose any path with the traffic, it will give you the final path of the minimum pollution versus minimum traffic, so that a person can have a good health index throughout the way and have a minimum resilience path to the pollution. So another model which we have developed with having our participatory node and few static nodes of the Jaipur region. These static nodes are from CPCB again, and these participatory node are the lab developed prototype models as shown in this figure. With these applications like Android app, we have shown you the entire label of India with this AQI, and you can see here this green zone is one of the picture taken at the initial phase of the first phase of the lockdown, and it is showing you the uh, before lockdown pictures where everything was red like thing. So in this model, the deployment is we have a cloud center and the edge devices. The edge devices are required for doing pre-processing and uh, downloading the transfer learning model for any individual who is moving from one place to another, and at that time the meteorological parameter changes, so the model governs for that particular area get changed. So these edge devices are helpful for a person like a participatory node who can move so dynamically during this uh, during these paths. And then this is the working model where we have used Jetson Nano as an our edge devices, and you can see here we are fetching data from these static nodes as well as the participatory nodes, and this video shows that the everything which we have done is in a form of a dockerized way, so that can be portably ported and deployed fastly. And this is a prediction model and showing you the output, and after this prediction numeric values plots the final uh, final graphs for individual participatory nodes who are contributing data to the server of Pilani. Thank you so much. I abruptly end my PPT here because the time is running out. But I welcome few questions, and I again thank the convener and all the organizers of this workshop and conference. And thank you very much.
Yeah, thank you. Yeah, over to the coordinator.
ஆன் பண்ணுங்க மேம். நான் பேசுறேன் சார். ஷேர் பண்ணுறேன் சார். நீங்க பேசு.
Thank you, sir. Thank you, sir.
Thank you, ma'am.
சார் பேசலாம்.
Thank you for your valuable information. Really, it was more useful. It will be helpful for us in our future. Thank you so much, sir.
Thank you. Yeah.
Any questions from online and offline participants? Any doubts? Excuse me.
Yeah, I'm there.
Thank you, sir. I request all participants, tomorrow's session will start at morning 9 o'clock. Offline participant students are requested to gather here sharp at 9 o'clock, 9 a.m. Refreshment is arranged at the back of this room. Thank you.
Can I leave the meeting now?